Hello viewers, good morning. I hope this video would find you in good health. And this time the topic is on nucleophilic substitution reactions from 2nd BSc Organic Chemistry. So we'll start with nucleophile. So what is a nucleophile? A nucleophile is a chemical species, that means electron rich chemical species that donates an electron pair to the electron deficient species to form a covalent bond. So, for example, all molecules or ions with a free pair of electrons or at least having one pi bond can act as a nucleophile. As the nucleophile have the capacity to donate electrons, they are also known as Lewis bases. And we have charged and neutral type of nucleophiles, and the examples for that are given below. Okay, so the nucleophile is an electron rich species which can donate electron pair to the electron deficient compounds. So the next one is, what is substitution? So substitution in general is known as replacement, and the substitution reaction is defined as a replacement of the already present functional group or an atom or a molecule in a chemical compound by a new incoming functional group or an atom or a molecule. And some of the conditions are mentioned here for the substitution reaction to takes place. Their maintenance of low temperature and the strong bond base which should be in low concentrations, and the solution needs to be in an aqueous state. So these are the conditions to be maintained for the substitution reaction to takes place. And next slide we can see what is a nucleophilic substitution reaction. A nucleophilic substitution reaction is a type of reaction where a nucleophile gets attached to the positively charged atom or molecule of the substrate. So these nucleophilic substitution reactions are the most common reactions which can be seen in alkyl halides. So why these are the common reactions in alkyl halides? Because the halogen atom and the carbon is having large electronegativity difference between them, and this electronegativity difference puts a partial positive charge on the alpha carbon atom and a partial negative charge on the halogen atom. So this partial positive charge makes the carbon susceptible for the attack by a nucleophile. So this is about nucleophilic substitution reactions. And next we have two types of nucleophilic substitution reactions, so depending upon the mechanism. So one is unimolecular nucleophilic substitution reaction, and the second one is bimolecular nucleophilic substitution reactions. Why they are called unimolecular and bimolecular means the rate of the reaction in unimolecular reactions, the rate of the reaction or the rate determining step, we can see only a single molecule. That's why it's called as unimolecular. Whereas in bimolecular substitution reactions, we can see two molecules. So it is called as bimolecular nucleophilic substitution reactions. So next, this is a diagrammatic representation of SN1 and SN2. And then this video actually covers a unimolecular nucleophilic substitution reaction and its mechanism. So SN1 reaction, in these are the nucleophilic substitution reactions in which the reaction follows the unimolecular mechanism. That means the rate of the reaction is directly proportional to the concentration of the alkyl halide, and it won't depend upon the concentration of the nucleophile. Okay, actually SN1 reaction it occurs in two stages. In the first stage, which includes ionization and formation of an intermediate carbonium ion, and the second step is the formation of a nucleophilic substituted product. So we know that these nucleophilic substitution reactions are mostly seen in alkyl halides. Among alkyl halides, the reactivity order is as follows: that is benzyl halides greater than allyl, greater than tertiary alkyl halides, greater than secondary, primary, and methyl halides. Okay. So why among the alkyl halides, generally tertiary alkyl halides are more reactive towards SN1 mechanism? This is why they are more reactive towards SN1 reactions, because here the we know that carboniamine is formed as an intermediate in unimolecular nucleophilic substitution reactions, and in when we observe tertiary alkyl halides, we can see the bulky alkyl groups attached to the center carbon, which can donate electrons due to plus I effect, inductive effect, so that the electron density at the halogen atom increases, which causes repulsion at the halogen atom, and hence it can be removed easily, thus forming a carbonium ion. This is the reason why tertiary alkyl halides are more reactive towards SN1 mechanism than the secondary and primary alkyl halides. So the next one is the mechanism. Here, as earlier said, it consists of two steps. The first one is the slow removal of the leaving group, forming carbonium ion. As it is a slow process, it is a rate determining step, and it includes a single molecule, so it is named as unimolecular mechanism. And the second step is the rapid attack of the nucleophile as soon as the intermediate carbonium ion is formed. Okay, so the first step is a slow step and the second step is a fast step. And here one more important thing we have to remember in the mechanism of SN1 reaction is that we know that carboniamine is formed as an intermediate. So these carbonium ions, they have some stability order like this. Tertiary carboniamine is more stable than secondary than primary. So while forming the product, while giving the product, the reaction may rearranges from a less stable carbonium ion to a more stable carbonium ion via 1,2 hydrate shift or 1,2 alkyl shift. Okay, because higher will be the stability of the intermediate carbonium ion, then higher will be the reactivity of alkyl halide toward SN1 mechanism. So this is the important thing we have to remember in SN1 reactions. And the next is we can see the different examples from here. Here we took hydrolysis of tertiary butyl chloride. So it's a slow reaction in which ionization takes place and gives tertiary butyl carbonium ion. And in second step, it reacts very fastly with nucleophilic solvent by giving alcohol product, tertiary butyl alcohol. So and we see another example, that is SN1 reaction of 2-bromo-3-methyl-butane, which follows SN1 reaction in which rearrangement takes place. So it gives a product as 2-methyl-2-butanol instead of a direct substitution product like 3-methyl-2-butanol. So it is better understood by going through the mechanism. So here when we take this reaction here, we have 2-bromo and 3-methyl butane. So it undergoes SN1 mechanism and it gives a secondary carbonium ion by the removal of bromide ion. So again it undergoes a rearrangement from 1,2 hydrate shift and it gives a tertiary carbonium ion, and again in the last step that tertiary carbonium ion reacts with the water to produce the rearranged tertiary alcohol, that means 2-methyl-2-butanol. So in this reaction we can see the rearrangement of less stable carbonium ion to a more stable tertiary carbonium ion. And so next comes the stereochemistry of SN1 reactions. So this SN1 reactions, actually we can see both type of products, that two types of products, that is product with inverted configuration as well as original configuration or retained configuration. So among the inverted and retained configuration products, inverted molecules are always in more number than the original configuration. This happens due to the fact that ionization of alkyl halide actually gives a carbonium ion halide ion pair. So already as the carbonium ion consists of a carbonium ion halide ion pair, this anion of the leaving group shields one side of the carbonium ion so that nucleophile attacks the carbonium ion from the opposite side of the leaving group. That's why it can easily attack the other side of the carbonium ion. So the inverted product predominates always than the product with retained configuration. Understood? So we can see from the stereochemistry that the SN1 reaction proceeds with the formation of inverted as well as retention of configuration. Here the inverted molecules are always in more number than the original products, original configuration products. This happens because the ionization of alkyl halide gives a carbonium ion halide ion pair, so that the nucleophile attacks the carbonium ion from the side opposite to that of the leaving group, as the leaving group shields the nucleophile from one side. That's why the inverted product predominates the one with retained configuration. This is about the stereochemistry of SN1 reactions. And the next thing is energy profile diagram of SN1. Here the energy profile diagram, it includes two transition states. Here we can see the diagram. So the reactants giving the first ionization, it is a transition state 1 with it is highly endothermic, so its activation energy is very high and it occurs very slowly. That's why it is called as a rate determining step. And the second one is the intermediate carbonium ion, and the third, it indicates the transition state 2 by the formation of the product by the nucleophilic attack on the carbonium ion giving the tertiary butyl alcohol. It is highly exothermic, so it occurs at low activation energy and therefore it occurs very fastly, and that's why the concentration of the nucleophile does not affect the rate of the reaction. So here EA1, it shows the first transition state, EA3 shows the second transition state. This is about the energy profile diagram of SN1 reaction. And the next thing is the factors affecting the rate of the reaction. So here we can see many of the factors, that is nature of substrate, effect of nucleophile, effect of leaving group, and the next one is effect of solvent. Here effect of substrate means we already heard in the beginning that tertiary alkyl halides, they are more reactive towards the SN1 mechanism rather than secondary and primary due to the presence of bulky alkyl groups. Okay, so this is how the substrate affects the rate of the reaction. And effects of nucleophile, here the strength of the nucleophile does not anyway affect the reaction rate, because in the rate determining step nucleophile is not involved, and effect of leaving group, as it is involved in the rate determining step, it has to be a good leaving group. Okay, if good leaving group is present, then the bond can be easily broken, and as soon as the bond is broken and carbonium ion is formed, the nucleophile will rapidly attack the carbonium ion by giving the nucleophilic product, substituted product. And the last one is the effect of solvent. So we have to use polar solvents, and including protic solvents like water or ethanol, so that the carbonium ion intermediate and the leaving group can be best stabilized by using polar solvents. So this is all about the factors affecting rate of reaction and the SN1 reaction and its mechanism. So I hope it's easy to understand this SN1 mechanism reaction examples through this video. So this is all about SN1 reactions, and thank you for watching this. If you like the video, please like button, and don't forget to subscribe this channel and keep watching my channel. And I'm going to upload SN2 reactions in my next video with some multiple choice questions, which would be very much beneficial to the students. Thank you.